Good day, I am Justoni Hindoy and today I am going to discuss about parallel pipe network system. And I'm going also to present an example based on different formulas such as Manning, darcy-weisbach, and hazen-williams formula. But before that, I'm going to explain first what is parallel pipe network system and what is the reason why we need it. So pipes are said to be in series if different lengths of pipes of different diameters are joined end to end with the entire flow passing through all pipes. Sometimes two or more pipes are connected so that the fluid flow splits among the branch pipes and eventually combine downstream into a single pipe. Such a piping system is referred to as parallel pipes. It is also called a loop piping system, where each parallel pipe is known as a loop. The reason for installing parallel pipes or loops is to reduce pressure drop in a certain section of the pipeline because of pipe pressure limitation or for increasing the flow rate in bottleneck section. By installing a pipe loop, we are effectively reducing the overall pressure drop in the pipeline from beginning to end because the flow is split through two pipes. So we are going to proceed now to our first example. So parallel pipe network problem number one, we are going to use Manning formula. So here is our illustration where the three pipes are parallel and also the properties of each pipe are also given. So problem number one, the discharge in pipe 3 is known to be 0.150 cubic meter per second and the roughness coefficient or N is equal to 0.15 for all pipes. So determine the following. A. The head loss in pipe 2, B. The head loss in pipe 4, and C. The flow rate in line 6. So since we're given the discharge in pipe 3, we can solve for the head loss for pipe 3. And in order for us to solve for the head loss in pipe 2, since pipe 2 and pipe 5 is the head loss in pipe 2 and pipe 5 is equal, and we can solve for the head loss in pipe 2, and the head loss in pipe 4 is just equal to the head loss in pipe 2 plus pipe 3. And to solve for the flow rate in line 6, the flow rate in pipe 4 and plus pipe 3 is just equals to the flow rate in line 6. So using Manning formula, which is equals to the major head loss is equals to 10.29 n squared L q squared all over d raised to 16 over 3. So since we are given the properties of the pipeline 3 and we are also given the discharge in pipeline 3, we can now solve for the major head loss in pipeline 3. So 10.29 times the roughness coefficient, which is 0.015 squared, times the length of pipeline 3, which is equal to 250 meters, times the discharge Q, which is equals to 0.150 squared, all over the diameter, which is 300 mm or 0.3 meters raised to 16 over 3. And we can, uh, the head loss, major head loss in pipeline 3 is equal to 8.06 meters. So since the parallel pipe 2 and pipe 5 is parallel, therefore we can say that head loss in pipe 2 is just equals to major head loss in pipe 5. Therefore, we can equate the two major head loss so that we can get the value of discharge pipe in terms of discharge 2. So we can solve now for the discharge in pipe 5, which is equals to 0.3486 Q2. So since the pipe 2 and pipe 5 is parallel and they combine in the pipe 3, Therefore, we can say that discharge from pipe 2 plus discharge 5 is just equals to Q3. So Q2 plus, since we have the value of Q5, which is equals to 0.3486, Q2 is equal to 0.150, we can also solve for discharge in pipe 2, which is equals to 0.111 cubic meter per second. Since we have the value now for our discharge in pipe 2, we can now solve for our head loss in pipe 2. Using the formula, major head loss 2 is equals to 10.29 times 0.015 squared times the length, which is equals to 310 meters, times discharge 2, which is equals to 0.11 squared, over the diameter, which is 200 mm or 0.2 meters raised to 16 over 3. And the value for our major head loss in pipe 2 is equals to 47.25 meters. So to solve for the value of the major head loss in pipe 4, so the major head loss in pipe 4 is just equals to head loss in pipe 2 plus the major head loss in pipe 3. So since we have the value for head loss in pipe 2, and also we have the value for major head loss in pipe 3, we can also solve for our major head loss in pipe 4. So 47.25 plus 8.006 is equal to 55.256 meters, which is the value of our major head loss in pipe 4. So since we have now the value of major head loss in pipe 4, we can now solve the discharge in pipe 4 in order for us to solve for the discharge in pipe 6. So substitute 55.256 is equals to 10.29 times our roughness coefficient, which is equals to 0.015 squared, times the length in pipe 4, which is equals to 1150 meters, times the discharge in pipe 4 squared, over the diameter, which is equals to 250 mm or 0.25 meters raised to 16 over 3. So the value of the discharge in pipe 4 is equals to 0.113 cubic meter per second. So as what I have said earlier, that the discharge in pipe 6 is just equals to the discharge in pipe 3 plus the discharge in pipe 4. So since we have the value for our discharge in pipe 3, which is equals to 0.150 cubic meter per second, and also we have the value for our discharge in pipe 4, which is equals to 0.113 cubic meter per second, we can also solve for the discharge in pipe 6. So the discharge in pipe 6 is just equals to 0.150 plus 0.113 is equals to 0.263 cubic meter per second. So in our problem number 2, in parallel pipe network problem, we will use the hazen-williams formula. So problem number 2, a parallel pipe network is drawn below. Water flows of 3 cubic feet per second enters in the parallel pipe network at junction P. All three pipes are scheduled 40 steel, and the diameter, length, and hazen-williams coefficients are shown in the following figure. So check if you can ignore minor losses. Compute the discharge in pipe 1, 2, and 3 in cubic feet per second. So here is our illustration. All the properties of pipes are given, or are also the hazen-williams coefficient, which is C, and also the discharge, which is equals to 3 cubic feet per second. So first we are going to write the relationship between all between three pipes. So the total discharge is equals to Q1 plus Q2 plus Q3, and the head loss in pipe 1, 2, and 3 are equal. So using hazen-williams formula, which is equals to 10.67 L Q raised to 1.85 all over C raised to 1.85 times D raised to 4.87. So now we are going to solve for our head loss one, since we are given all the properties that we need except for the discharge. So we are going to solve for the major head loss in each pipe in terms of its discharge. So, and the major head loss in pipe 1 equals to 10.67 times 200, which is the length, times the discharge raised to 1.85 over C, which is equals to 80, over raised to 1.85 times its diameter, which is equals to 0.1167 raised to 4.87, is equals to 3925.08 Q1 raised to 1.85. So the major head loss in pipe 2, which is equals to 10.67 times the length, which is equals to 100 times Q2 raised to 1.85 all over all over C, which is equals to 50 raised to 1.85 times 0.50 raised to 4.87, and the major head loss in pipe 2 is equals to 22.44 Q2 raised to 1.85. So the major head loss in pipe 3 is equals to 10.67 times uh, length, which is equals to 100 times Q3 raised to 1.85 over C, which is equals to 100 raised to 1.85 times 0.33 raised to 4.87. So the major head loss in pipe 3 is equals to 45.07 Q3 raised to 1.85. So since we have the relationship in pipe 1, 2, and 3, so we can equate the major head loss in pipe 1 and pipe 2, so that we can solve for the discharge in pipe 2 in terms of Q1. So 3925.08 Q1 raised to 1.85 is equals to 22.44 Q2 raised to 1.85. So since we are going to solve for Q2 in terms of Q1, so 3925.08 divided by 22.44 is equals to 174.88. And then we are going to solve for Q2. So we need to take the 1.85th root of both sides. So Q2 is equals to 16.304 Q1. So since uh, the relationship between the three pipes is equal, we can also solve, or we need also to solve we need also to solve for Q3 in terms of Q1. So therefore, we need to equate the major head loss in pipe 1 and major head loss in pipe 3. So 3925.08 Q1 raised to 1.85 is equals to 45.07 Q3 raised to 1.85. So since we are going to solve for Q3 in terms of Q1, we need to divide 3925.08 divided by 45.07 is equals to 87.09 Q1 raised to 1.85, and take the 1.85th root for both sides. So Q3 is equals to 11.19 Q1. Since we have the relationship of the discharge in our illustration, so the total Q is equals to Q1 plus Q2 is equals to Q3. So since we are given for the discharge total, which is equals to 3 cubic feet per second, we can now solve for our Q1. So 3 cubic feet per second is equals to Q1, and we have the value for Q2, which is equals to 16.304 Q1, plus Q3, which is equals to 11.19 Q1. Then we can solve for Q1, which is equals to 0.1053 cubic feet per second. To solve for Q2, we just need to substitute Q1 in our equation for Q2. So 16.04 times Q1, which is equals to 0.1053. So Q2 is equals to 1.72 cubic feet per second. And to solve for Q3, since we have our equation for Q3 in terms of Q1, we can also substitute Q1 to our equation. So Q3 is equals to 11.19 times Q1, and Q3 is equals to 1.18 cubic feet per second. So parallel pipe network problem number 3, we are going to use darcy-weisbach formula. So problem number 3, pipelines 1, 2, and 3 are connected with parallel to each other. The three pipes carries a combined discharge of 0.86 cubic meter per second. So assuming F or friction factor of 0.02 for all pipes, compute the head loss in pipe 1 and the discharge in pipe 2 and 3. So here is our illustration, and we are also given the properties of pipes and F or the friction factor. So the relationship between pipe 1, 2, and 3 and the discharge, total discharge, and the discharge in pipe 1, 2, and 3. So the uh, total discharge is equals to the discharge in pipe 1 plus discharge in pipe 2 plus the discharge in pipe 3. And the major head loss in pipe 1, 2, and 3 are also equal. So using darcy-weisbach formula, which is equals to HF equals to 0.0826 FLQ squared all over D raised to 5. So we are also going to find the value of major head loss in terms of each discharge. So the major head loss in pipe 1 is equals to 0.0826 times the friction factor, which is equals to 0.02 times length, which is equals to 700 times the discharge in Q1 squared over D raised to 5, or 0.45 raised to 5 is equals to 62.67 Q1 squared. The major head loss in pipe 2 in terms of Q2 is equals to 0.0826 times 0.02 times 800 Q2 squared all over 0.4 raised to 5, which is equals to 129.06 Q2 squared. So the major head loss in pipe 3 in terms of Q3 is equals to 31.718 for Q3 squared. And since we have the relationship between the major head loss in pipe 1 and 2, so therefore we can solve for Q2 in terms of Q1. So we are going to equate the major head loss in pipe 1 and 2. So 62.67 Q1 squared is equals to 129.06 Q2 squared. And since we are going to solve for Q2 in terms of Q1, we need to divide 62.67 over 129.06, which is equals to 0.4856, and take the square root for both sides. So Q2 is equals to 0.697 Q1. So since we are going to solve for the discharge 1, we need also to find the discharge or Q3 in terms of Q1. So we need to equate also the major head loss in pipe 1 and the major head loss in pipe 3. So 62.67 Q1 squared is equals to 31.72 Q3 squared. And since we are going to find the discharge in pipe 3 in terms of Q1, we need to divide 62.67 over 61.72, which is equals to 1.976 Q1 squared. Take the square root for both sides, so Q3 is equals to 1.406 Q1. So since we have the value now for Q2 in terms of Q1 and Q3 in terms of Q1, we can now solve for our Q1 since we have that uh, value for our Q total. So the value for our Q total is 0.86 cubic meter per second. So 0.86 equals Q1 plus 0.697 Q1 plus 1.046 Q1. So we can solve now for our Q1, which is equals to 0.277 cubic meter per second. So since we are asked to find the major head loss in pipe 1, so we can now solve for the major head loss in pipe 1 since we have the value now for our Q1. So the equation to solve for the major head loss in pipe 1 is equals to HF1 is equals to 62.67 Q1 squared. So we just need to substitute the value of Q1 in this equation. So 62.668 times 0.277 squared. So the major head loss in pipe 1 is equals to 4.82 meters. Next is since we have the value for our Q1, we can now solve for the value of Q2 since we have the equation for Q2. So the Q2 is equals to 0.697 Q1. So substitute the value of Q1, we can solve now for the value of Q2, which is equals to 0.193 cubic meter per second. Q3 is equals to 1.406 Q1. So substitute also the value of Q1, we can now solve for the discharge in pipe 3. So 1.406 times 0.277. So the value for the discharge in pipe 3 is equals to 0.39 cubic meter per second. Since we're done discussing about parallel pipe network system, I am going to discuss now about the three reservoir problems and provide also different problems based on different formula such as Manning, hazen-williams, and darcy-weisbach formula. But before that, I'm going to explain first the importance of reservoir. So reservoir are artificial lakes created by the construction of dams across rivers. They are also called storages. These are developed to retain excess water during period of high flow for use during periods of drought or demand. Reservoir mainly serve the purposes of water conservation and flood control. So we are now going to proceed to our first example. So reservoir problem number 1, we are going to use darcy-weisbach formula. So situation number 1, three reservoir A, B, and C are connected respectively with pipes 1, 2, and 3, joining at a common junction P. Reservoir A is at elevation 80 meters and reservoir B at elevation 70 meters and reservoir C is at elevation 60 meters. And the properties of each pipes are as follows. So pipe 1, length is 5,000, diameter is 300 millimeters. Pipe 2, 4,000 meters and the diameter is 250 millimeters. Pipe 3, the length is 3,500 meters and the diameter is unknown. So the flow from reservoir A to junction P is 0.045 cubic meter per second, and the friction factor for all pipes is 0.018. So we are given here the discharge from reservoir A to junction P. So question number 1, find the elevation of the energy grade line at P in meters. So we are asked here the elevation of the piezometer reading. Then question number 2, determine the flow on pipe 2 in cubic meter per second. And question number 3, compute the diameter appropriate for pipe 3 in millimeters. So that's why we don't have a diameter here. So first we are going to list down what are given. So reservoir A elevation is 80 meters, reservoir B is 70 meters, and reservoir C is 60 meters. And the friction factor for all pipes is 0.018, and the discharge from reservoir A is 0.045 cubic meter per second. So also the properties of pipes are listed down here. So here is our illustration. So the based on the problem. So elevation A is 80 meters. Elevation from of reservoir B is 70 meters, and reservoir C elevation is 60 meters. So the flow from reservoir A to junction P is obviously going downward because it has the highest elevation. So also the uh, direction of flow from junction P to reservoir C is also going downward. But here in reservoir B, we don't know the direction of flow exactly because uh, here we are going to assume that the direction of flow from junction P to reservoir B is going to reservoir B. So therefore, the elevation of piezometer reading should be from elevation A and elevation B. Therefore, the elevation of piezometer reading is from elevation 70 to 80. And we are asked here to find this elevation. So using darcy-weisbach formula, which is equals to major head loss is equals to 0.0826 friction factor times LQ squared over D raised to 5. So since we are given here the discharge A, we can now compute the head loss 1. So 0.0826 times friction factor, 0.018 times 5,000 times the discharge A 0.045 squared all over the diameter, which is equals to 300 mm or 0.3 meters raised to 5. So therefore, the value of major head loss 1 is equals to 6.195 meters. So since we have now the value of major head loss 1, we can now compute for the value of piezometer reading. So elevation of P prime is just equals to elevation A minus the major head loss. So elevation A is 80 meters minus the major head loss 1, which is equals to 6.195. Therefore, the elevation of piezometer reading is equals to 73.805 meters. So it's stated here that the energy at P, denoted as P prime, is higher than the reservoir B, thus the flow in pipe 2 is towards B. So what we assume is correct. So here, since we are asked to find the flow rate in reservoir B, so we are now going to find the major head loss in pipe 2 in order for us to solve the discharge in pipe 2. So the head loss in pipe 2 is just equals to the elevation of P prime or the elevation of piezometer reading minus the elevation of B, which is equals to 73.805 minus 70. So the major head loss 2 is equals to 3.805 meters. So since we have now the value of the major head loss 2, we can now compute for the discharge 2 or the flow rate. So 0.0826 times friction factor 0.018 times 4,000, which is the length, times Q2 squared raised to all over 0.25 raised to 5 is equals to the major head loss 2, which is equals to 3.085. And therefore, the value of discharge 2 is equals to 0.025 cubic meter per second. So at junction P, inflow is equals to outflow. So the inflow here is Q1, since only the Q1, the direction of flow of Q1 is towards junction P, while the direction of flow in uh, reservoir B and C is the towards the reservoir. So Q1 is equals to Q2 plus Q3. So 0.045, which is our Q1, which is given, is equals to Q2 0.025 plus Q3. So therefore, we can solve now for our Q3, which is equals to 0.02 cubic meter per second. Next is we are going also to solve for the value of major head loss 3. So elevation of P prime, or the elevation of piezometer reading, minus the elevation C, which is equals to 73.805 minus 60. So therefore we can solve now for the major head loss 3, which is equal to 13.805 meters. So uh, we need to solve for Q3 and major head loss 3 in order for us to solve for the diameter of pipeline 3. So since we have now the value of Q3 and major head loss 3, we can now solve for the diameter in pipeline 3. So 0.0826 times 0.018 times the length of pipeline 3, which is equals to 3,500, times the 0.02 squared, which is the discharge in pipeline 3, all over the diameter raised to 5 is equals to our major head loss 3, which is equals to 13.805. Therefore, the diameter in millimeters in pipeline 3 is 172 millimeters. So problem number 2, we are going to use hazen-williams formula. So from the given three reservoirs shown, the elevation A is 345 meters, B is at elevation 300 meters, and C is at elevation 240 meters. Then the rate of flow at 1 is 200 liters per second. So question A is compute the head loss in pipeline 2 and the discharge in pipeline 3. So in the table we are given the properties of pipes and hazen-williams coefficient C. So using the formula, major head loss is equals to 10.64 LQ raised to 1.85 all over C raised to 1.85 times diameter 4.87. So since we are given here the flow rate at pipe 1 or reservoir A, that is equals to 200 liters per second or 0.2 cubic meter per second, we can now solve for the major head loss 1. So this is major head loss 1. So major head loss 1 is equals to 10.64 times length, which is equals to 700, times the value of discharge, which is equals to 0.2 cubic meter per second raised to 1.85, all over C, which is equals to 120 raised to 1.85 times diameter 400 mm, or 0.4 meters raised to 4.87. So therefore the value of major head loss 1 is equals to 4.62 meters. So since we don't know the direction of flow here in the middle reservoir, we are going to assume that the direction of flow is towards reservoir B. Therefore, the the elevation of piezometer reading should be here, or between the elevation of reservoir A and reservoir B. So therefore, we can say that uh, reservoir A, the elevation of reservoir A minus the elevation of reservoir B is just equals to major head loss 1 plus major head loss 2. So since we have now the value of major head loss 1, we can now solve for our major head loss 2. So substitute the 4.682 meters here, and the value of our major head loss 2 is 40.318 meters. So the discharge in pipeline 3. So using the formula 10.64 L Q raised to 1.85 all over C 1.85 times D 4.87. So since we have now the value of the major head loss 2, we can now solve for the discharge in pipeline 2. So we need to find this value because we have the relationship which is equals to Q1 is equals to Q2 plus Q3. So since we have the value of Q1, we need to find the value of Q2 in order for us to find the discharge in pipeline 3. So since we have now the value in major head loss 2 in pipe 2, so we can now solve for major discharge in pipe 2. So 40.318 is equals to 10.64 uh, times 2100, which is the length, times Q2 raised to 1.85 all over C, which is equals to 100 raised to 1.85 times diameter 0.31 meters raised to 4.87. So the discharge in pipeline 2 is equals to 0.151 cubic meter per second. So since the elevation of piezometer reading is between elevation A and elevation B, and we assume that the flow from the middle reservoir is towards the reservoir. Therefore, we have this equation Q3 is equals to Q1 minus Q2. So since we have now the value of Q1 which is given, and the value of Q2 which is equals to 0.151, therefore we can now solve for the value of Q3. So Q3 is equals to 0.2 minus 0.151 is equals to 0.049 cubic meter per second. But we are asked for the value of Q3 in cubic feet per second. Oh, liters per second. So Q3 is equals to 49 liters per second. So problem number 3, we are going to use Manning formula. So from the sketch below, and using Manning's formula, determine the following. So A, the flow into or out of reservoir A, or the discharge in reservoir A in liters per second, discharge in reservoir B, and C in liters per second. So the, here is our illustration. So the elevation of reservoir A is 33 meters, elevation of reservoir B is 24.4, and the elevation of reservoir C is 15.2. And we are also given here the properties of each pipe. So the direction of flow from reservoir A is obviously going to the junction, since the reservoir A has the highest elevation. And the direction of flow from junction to reservoir C is obviously going downward, since reservoir C has the lowest elevation. But here in reservoir B, we don't know exactly what is the direction of flow. Therefore, we are going to assume that uh, the direction of flow from junction to reservoir B is going to the reservoir. So, if that's the case, so the elevation of piezometer reading should be between elevation A and elevation B. And therefore, we can solve for the head loss headless 1, headless 2, and headless 3. So first, we're going to list down the given. Since we're going to find the discharge in reservoir A in liters per second. So our assumption here is, since the direction of flow is going to reservoir B, therefore QA inflow is equals to outflow, which is equals to QB plus QC. And our head loss 2, which is here, is equals to 8.6 minus H1. So we are going to find the head loss 2 and head loss 3 in terms of H1. So using Manning formula, HF is equals to 10.29 n squared LQ squared all over diameter 16 over 3. So rearrange the formula so that we can solve for Q. And since all this value, all of this has a constant value, we can separate it and express it as K. So Q is equals to K times the square root of H. So first we're going to solve for Ka. So square root of uh, diameter, which is equals to 300 mm, so 0.3 raised to 6 over 3 over 10.29, 0.011 squared, or the roughness coefficient n times the length is equals to 1220. So Ka is equals to 0.0327. So the Kb, so square root of 0.25 raised to 16 over 3 is equal, all over 10.29 times the roughness coefficient times length, which is equals to 500 meters. So Kb is equals to 0.0314. Kc is equals to square root of 0.135 raised to 16 over 3 over 10.29 times 0.011 squared times the length, which is equals to 1520. So Kc is equals to 3.49 times 10 raised to negative 3. So since we assume that Qa is equals to Qb plus Qc, or inflow is equals to outflow, we can now solve for H1. So since Qa is equals to K times square root of H, and we, our assumption there, uh, we solve the H2 and H3 in terms of H1. So therefore, we can solve for H1. So Ka is times square root of H1 is equals to Kb times square root of 8.6 minus the H1, and Kc times the square root of 17.8 minus the H1. So the value of H1 here is 4.9342 meters. So since we have now the value of H1, we can now solve for the flow rate in reservoir A. So here is our illustration equation to solve for the discharge in reservoir A. So Qa is equals to Ka times the square root of H1. So 0.0727 is our final answer. But we are asked to find the discharge in reservoir A in liters per second. So 0.0727 cubic meter per second times 1000 liters over 1 cubic meter. So the discharge A is 72.69 liters per second. So same here for the discharge in reservoir B. Since we have now the equation to solve for the discharge in reservoir B, so we just need to substitute the value of H1 in this equation. So QB is also KB times square root of 8.6 minus H1. So QB is equal to 0.0 602 cubic meter per second, and convert convert this into liters per second. So QB is equals to 60.19 liters per second. Same here for uh, the discharge in reservoir C or QC. So the discharge in QC is equal to 12.51 liters per second.